Hello everyone, my name is Ross Steenson with the San Francisco Bay Regional Water Board, and in this segment we're going to cover attachments 1 through 4 of the Supplemental Vapor Intrusion Guidance, or SVIG. The 4 attachments are, in order, number 1, lines of evidence, number 2, petroleum-specific considerations, number 3, sewers and other vapor conduits as preferential pathways for vapor intrusion. And number 4, groundwater as a line of evidence to evaluate vapor intrusion risk. Attachment 1, the lines of evidence attachment, covers the following. Defines what a line of evidence, or LOE, is. It discusses the weighting of a line of evidence and weighing or integrating multiple lines of evidence. It also provides a description of the typical lines of evidence used in developing conceptual site models, along with some discussion of some more recent, less frequently used testing methods. This attachment is new and it was added in response to comments on the February 2020 draft SVIG. A line of evidence is a fact or other information determined by any of the following: direct observation, such as a building survey, interviews with knowledgeable persons, review of records and documents such as aerial photos, Phase 1 environmental assessments, or other reports, the sampling and analysis of environmental media such as indoor air, outdoor air, soil gas, results of research and testing, or a statistical or other type of analysis such as empirical databases. Each of these is referred to as its own line of evidence. And it's important to keep in mind that these can be either qualitative or quantitative. The benefits of using multiple lines of evidence is that it results in an improved understanding of vapor intrusion at our site. It increases confidence in our decision-making regarding the VI pathway, and it reduces the overall uncertainty, particularly when some lines of evidence may have significant uncertainty. The classic situation where we need multiple lines of evidence for VI is the interpretation of indoor air results, where we can have indoor air data, outdoor air data, the building survey results, subslab or other subsurface type of data, or crawl space air data, site history. We may additionally have utility location information and vapor conduit air data, and all of these have to be weighted and weighed to interpret whether VI is occurring at a given site or building. When using multiple lines of evidence, one of the things you're going to have to do is figure out how much weight or importance you're going to assign to a given line of evidence. To think about this, we're going to walk you through 3 factors, with the first being relevance. That gets at how much does the line of evidence help you address the question being asked. To speak to this, I'm going to use this cross-section down below. Let me explain it to you. So on the right, we have a dry cleaner. There's been a release of PCE, and it's contaminated the underlying soil, and it's reached groundwater, and it's flowing. We have a groundwater plume flowing off to the left into a neighborhood with residences. So question might be, how relevant are the groundwater data for evaluating the VI pathway? And the answer is, it depends. So for the dry cleaner building, it's not so helpful or relevant because there's overlying soil contamination. In that situation, indoor air and subslab soil gas are going to be more relevant lines of evidence. Essentially, from an SVIG perspective, you'd be starting with step 3. Moving off to the left into the neighborhood, the groundwater data become a more relevant line of evidence because it's the local vapor source. You don't have the overlying soil contamination, right? So next factor I'd like to mention is representativeness. And this gets at whether the information accurately replicates site conditions or the question being asked. So let's take indoor air sampling. Would sampling in a bathroom only be indicative of long-term risk to occupants? And the answer is probably not, unless they spend most of their time in the bathroom. So generally, we might sample in a bathroom to evaluate whether VI is occurring or the vapors are entering it in the bathroom, but when it comes to evaluating long-term risk or chronic risk, we generally want to collect samples in the most routinely occupied spaces. Third factor is quality, and this is whether the sampling or analysis was performed using an accepted protocol. So an example might be where the soil gas samples collected in accordance with the active soil gas advisory into the quality control checkout. Key thing to keep in mind is that the same line of evidence could be weighted differently at a different site, or a different building at the same site, or even for the same building if the situation is different. For instance, maybe the HVAC is operating versus not, right? Or even separate sampling events. So when weighting a line of evidence, context is critical. So after you have weighted individual lines of evidence, you have to weigh or integrate those lines of evidence together to make an interpretation, right? And it's important to keep in mind that not all lines of evidence are likely to agree. If a line of evidence or lines of evidence don't agree, you shouldn't automatically dismiss them. You should try to explain them, why they're not in agreement. And as you add lines of evidence, the conceptual site model should be updated. The lines of evidence attachment describes a number of LOEs, and we've grouped them into the following categories. Site characteristics, which includes aspects of the site history, the building condition, subsurface conditions. The site characterization LOE, which is really the soil gas and the groundwater data and or air data. Contamination characteristics, is the source a dilute solution or was it actually non-aqueous phase liquid that was released? Contaminant properties. Weather meteorological conditions, and then we cover a number of other LOEs such as models, the use of models, and other measurement techniques. On this and the coming slides, I'm going to go over some of the categories and individual lines of evidence. Here we have building characteristics, and this is one of the factors that makes evaluating the vapor intrusion pathway challenging. And so think about the design and construction, and we can make some general characterizations about susceptibility. So on this chart on the right, we have at the bottom, we have the dirt floor basement listed as being the most susceptible to vapor intrusion. This is because it has a lot of surface area in contact with the soil, and part of it is unpaved, allowing potentially higher soil vapor entry rates. Kind of stepping up from that, we have slab on grade, which only has the slab in contact with the soil. Crawl space is offset from the soil, and so there is some space for potential dilution. I have to consider how open that space is, how well ventilated that space, and whether there may be fresh air intakes in that space. Subterranean garages, on the one hand, have a lot of surface area in contact with the soil. They're of course concreted, and they also have ventilation, at least to prevent carbon monoxide buildup, which should help alleviate potential vapor intrusion to some extent. Open air garages are considered the least susceptible because they have quite a bit of height between the soil and the occupied spaces above, and so there's plenty of room for air dispersion and movement. Another factor to think that may affect is where the entry points, vapor entry points in pathways such as elevator shafts or sumps. The condition of the building is really important. So buildings that have been damaged may be more susceptible. Buildings that have been renovated and potentially maybe the floor hasn't been put back in the spaces behind the walls, that may increase the susceptibility to vapor intrusion. And lastly, there's ventilation, and this gets at how the windows and doors are used, whether there's an HVAC system and how it's operated, and whether there are exhaust fans that locally could depressurize and induce vapor intrusion. So all these things can be factored in or have to be thought about whether a building is susceptible to vapor intrusion or not. So next, let's cover the subsurface conditions line of evidence. Here we're going to break this into geology and stratigraphy first. And so what we're thinking about are soil types and their characteristics. So for soil types, we're thinking whether it's coarse or fine-grained. And then in terms of characteristics, let's kind of focus on moisture content here, because that is the dominant control on vapor transport in the subsurface. So at higher moisture contents, vapors diffuse more slowly and it basically attenuate more sharply through those soils, leading to reduced potential for vapor intrusion. This is particularly true for the finer grained soils because they have the ability to hold, in general, greater water content at field conditions than coarser grained units. In terms of continuity, so if we have continuous fine-grained layers, considering their characteristics of generally having higher moisture contents, that's going to lead to reduced potential for vapor intrusion or vapor migration. If those layers are not continuous, then potentially the vapors are going to be able to move around those layers. And so that's the key thing in terms of continuity. You may recall that for the groundwater screening attenuation factor from US EPA, there's an alternative for a slightly lower attenuation factor when there are continuous fine-grained layers. In terms of anthropogenic influences, here we've just listed a few and they have kind of different potential effects. So grading, filling, utility trenches, these things are going to change the vapor migration characteristics of the subsurface. They may break up the soil structure, break up that continuity. The presence of buildings or hardscape can, result to some extent in the capping effect, or may result in the capping effect. Irrigation is going to introduce more water into the subsurface, so it's going to increase soil moisture and at least locally or temporarily result in less vapor migration. In terms of groundwater, we're thinking about what's the water table depth, how much vadose zone do we have to work with, what are the range of fluctuations, and it's also important to keep in mind capillary fringe thickness, which is partly a function of the soil type. So finer grained soils near the water table are going to have much thicker capillary fringes, and this is a high moisture zone, again, resulting in less vapor migration, greater attenuation. And then we have potential preferential pathways. Obviously, there are natural preferential pathways such as fractures or gravel layers or gravel backfill, but then we also have vapor conduits. And again, what we're talking about when we say vapor conduits is we're talking about essentially unimpeded or nearly unimpeded vapor transport through the airspace of a pipe or a conduit. So for this slide, I just wanted to bring to attention that the lines of evidence attachment discusses all of these contaminant characterization lines of evidence. And so you can consult that on your own time, perhaps as you need to use these for your individual sites. On the coming slides, I'm going to talk a little bit about how the soil matrix data line of evidence can be used and its limitations. So for the soil matrix data line of evidence, it's not used directly for evaluating the potential for vapor intrusion. For that, we want soil gas or indoor air data primarily. But it can still be helpful as part of the evaluation to identify source areas and/or their extent, potentially the presence of NAPL, planning for soil gas sampling. And for situations where you can't get soil gas samples due to low permeability soil or it's locally saturated, supplementing with some soil matrix data could prove helpful. And then there's some other uses, for instance, if you need to assess risk for the direct soil exposure pathway. So let's wrap this up with limitations of soil matrix data for evaluating vapor intrusion. Loss of volatiles both before and after the sample collection all the way to the time of analysis is the major issue, and this volatile loss can be significant. As a result, samples should be collected quickly and preserved in accordance with US EPA method 5035. This method, which originally released by US EPA in 1999, and then DTSC published this 2004 guidance document promoting its use in California. So non-US EPA method 5035 data, soil data, which primarily includes everything before the DTSC document, in general should not be heavily weighted as a line of evidence for vapor intrusion evaluations. We still see that some samples, VOC samples today, are not analyzed for 5035, so be sure to keep an eye on that for your own projects. The other major issue is soil matrix heterogeneity, and so soil samples that are collected over just short distances away, centimeters or feet, yards, can have a wide variation in concentration. For further reading on these topics, we point you to this US EPA 2014 engineering issue. So for contamination characteristics, lines of evidence, the three aspects we're going to cover. So first is source type and strength. So non-aqueous phase liquid, or NAPL, would be expected to be a high strength source generally, whereas what's dissolved in groundwater or in dilute solutions such as NAPL mixed with another solvent like water, diesel, or oil would be kind of a lower strength source. Contamination or contaminant chemical and physical properties can be really important for understanding potential for VI. So, think about volatility, and, in that case, we're talking about vapor pressure for volatilization from the actual NAPL, or Henry's law constant for volatilization from the water phase, be it soil moisture or groundwater, as well as other factors such as solubility, absorption, etc. Vapor transport mechanisms. Remember that diffusion is the dominant vapor transport mechanism in the subsurface, and the transport direction is from high concentration to low concentration. And that chemical diffusion through water occurs at a much lower rate, orders of magnitude lower than diffusion in air, which is why soil moisture has a major influence on the potential for vapor intrusion, as we mentioned in earlier slides. Advection is where the transport is from high pressure to low pressure, and for the typical situation for VI, this happens only in the immediate vicinity of the building, where there's higher pressure in the subsurface, and potentially the building itself is depressurized due to the stack effect. So digging a little deeper into contaminant chemical and physical properties. First up, just a reminder that the SVIG uses the same definition as US EPA for that of a volatile chemical in terms of vapor pressure and the Henry's law constant. Here we have a table of tetrachloroethene, PCE, trichloroethene, TCE, cis-1,2 dichloroethene, and VC or vinyl chloride. Just wanted to point out a couple of interesting differences. So for taking PCE and TCE, if you look at compare the vapor pressures, TCE is about three times the vapor pressure of TCE, meaning it has kind of a greater propensity to volatilize from the NAPL phase. We have slight reverse situation in terms of the Henry's law constant, with PCE about twice the propensity to volatilize from groundwater. And then comparing both of those to vinyl chloride, it has a much, much higher vapor pressure and Henry's law constant. Really wants to be in the vapor phase and highly volatile contaminant. Moving on to the weather meteorological condition lines of evidence, just want to touch on a few things. Barometric pressure, temperature effects. There's also wind effects, which we're not going to cover. And so on the left, we have the classic illustration of the stack effect. So we have cold air outside, perhaps it's winter. You have a building, the building is being heated. Warm air rises, warm air is less dense, draws in cool air from the subsurface. So vapor intrusion potentially is kind of on here. And this is why we often want to see a round of sampling, indoor air sampling, during the cooler seasons. On the right, we have a graph that's taken from one of these continuous monitoring investigations where they've plotted barometric pressure in the kind of dark gray or in the gray color and TCE concentration in indoor air in a kind of a bluish color. And you can see that the TCE spikes correlate with drops in barometric pressure. And these types of investigations aren't done at every site, but often done when the indoor air results it's not clear what's going on at a site, and they come in and do this as follow-up work. Mathematical models can also be used as a line of evidence, and here we put together some of the use considerations. So models are best used when you have a well-developed conceptual site model, and also you have site-specific data for key parameters. The use of models in the refined risk assessment is discussed in SVIG Step 4. Some of the considerations when using models as a line of evidence is including uncertainty analyses to help understand the range of potential outcomes. In addition, using them possibly to support but not be the sole line of evidence in developing cleanup goals. The possibility of collecting confirmation indoor air samples to verify results or predictions, or using multi-depth soil gas samples to kind of figure out empirically how much attenuation is actually taking place in the subsurface. Models are generally best not used for initial screening of occupied buildings when you really don't have a lot of information about a site. This is discussed in the SVIG introduction. I've referenced the specific section. When you have non-homogeneous subsurface conditions, for instance, the geology is very complex. When preferential pathways are not ruled out, when sources are shallow, right? And when conditions are changing, such as plumes are migrating. So over the last decade or more, there have been a number of newer testing methods that have been suggested that are promising in evaluating the vapor intrusion pathway. We've provided descriptions of a number of these in the lines of evidence attachment, along with some considerations for their use. For instance, indicators, tracers, and surrogates, continuous monitoring, where samples are collected very frequently over a few-day campaign. They might include indoor air, subslab, barometric pressure, temperature measurements, and some of these other methods. Some of the things to keep in mind are, most of these methods are not verified by US EPA or Cal EPA. So it's going to be incumbent for the regulators to have a work plan to be able to review, and they're probably going to have to consult their colleagues that may or may not be familiar with this. And so these methods are best used as another line of evidence, and be aware that acceptance can vary among stakeholders and might require a fair bit of communication if this line of evidence or these lines of evidence are being heavily weighted. So in terms of these other lines of evidence, one line of evidence we get a lot of questions about, and that's radon. Can it be used essentially as a surrogate for VOCs or VFCs, and especially to determine site-specific attenuation factors? So on the plus side, it's a gaseous product that does not, it's not reactive, and it can be measured in the laboratory, but also with some field instruments. However, in terms of contrast versus volatile organic chemicals, the source and distribution differ. Radon is more widely distributed versus the VOC sources. The transport mechanism from soil gas to indoor air is generally similar, but there are some differences in characteristics. This slide points out a couple of uses for radon as a line of evidence. So one is evaluating building susceptibility to VI. And in this situation, you would measure indoor air radon and soil gas radon at multiple buildings to see whether radon concentrations are higher in certain buildings, and you could go prioritize those for VFC indoor air sampling. Another option is to see if you can monitor radon and VFCs and soil gas and indoor air over time. See if there's a correlation. Is radon a good indicator when it increases, whether VFCs are increasing? And then you could use radon in an ongoing manner to determine when to sample VFCs and indoor air when VI is occurring. Lastly, limitations. So radon is not considered a good surrogate for VFCs. So the changes in radon concentrations typically are not proportional to changes in VFC concentrations, so we would not necessarily use radon attenuation factors as a exact match for VFC attenuation factors. Now, if you conducted this evaluation above, where you monitored radon and VFCs and soil gas and indoor air over time, and you found those attenuation factors, at multiple locations over time, and you found those to match, that might mean that for that particular site or that particular building, maybe it is a good surrogate, but just in general, it's not. Okay, folks, let's wrap up attachment 1, lines of evidence, with Jessica's and Nicole's tricolor diagram. Let me explain how this is set up. Down the middle, we have lines of evidence, or selection of lines of evidence. On the right, we have kind of two different considerations. One is high VI potential or high uncertainty, not the same thing. So keep in mind, if what you read doesn't match one, it probably matches the other, right? And on the left, low VI potential or low uncertainty. So I'm not going to go through every one of these, but let's pick a few. Environmental persistence. So chemicals that are not persistent or have low persistence are going to, in general, have lower VI potential, right? Chemicals that are persistent are going to have a greater VI potential. So our classic examples for the right would be chlorinated VFCs, and on the left would be petroleum VFCs. Let's take proximity to contaminated media. So there's going to be higher VI potential if the contaminated media is closer to a building, vertically or laterally, than if it's far away. Let's take modeling. So, if there's no empirical data, we're just kind of using a generic model and some generic soil layers, and we don't have good cross sections to match that up, there's going to be greater uncertainty associated with that than for a situation where we've got good control on the geology, the soil layers, soil parameters, and we have essentially as many inputs as we can controlled, right? And then lastly, let's take offsite source contamination. So if you have an offsite source, if that source is not controlled, and potentially it's feeding a groundwater plume that's coming onto your site, you're going to have greater uncertainty and probably greater VI potential than you would otherwise, right? So that wraps up lines of evidence. Attachment 2 presents the petroleum-specific considerations when using the supplemental VI guidance. The attachment covers the following: the objectives, background on petroleum hydrocarbon biodegradation, description of 2 different PVI or petroleum vapor intrusion screening approaches, and the use of these approaches in steps 1 through 4 for non-UST petroleum sites. This attachment was significantly revised in response to comments on the draft SVIG. The primary objective of Attachment 2 is to promote approaches to petroleum vapor intrusion screening at non-underground storage tank petroleum release sites that are similar to the approaches in the State Water Board's low-threat UST case closure policy. The second objective is to describe how to use these PVI screening approaches in conjunction with the SVIG. This slide serves as a comparison and contrast between petroleum vapor intrusion and chlorinated vapor intrusion. We have identical release scenarios, one on the left for petroleum VFCs released from an underground storage tank, and on the right, release of chlorinated VFCs from an underground storage tank. However, there's some distinct differences. So you can see on the left that NAPL, non-aqueous phase liquid, has traveled or migrated through the vadose zone and pooled on top of the groundwater, and so we have L-NAPL. They're both vapor phase and dissolved phase hydrocarbon plumes, but their extent is relatively limited as compared to the chlorinated VFC release on the right. And this is due to biodegradation. So petroleum hydrocarbons are susceptible to biodegradation, and this serves to slow and limit the migration of petroleum hydrocarbons in both soil vapor and groundwater. So let's cover a little bit more regarding biodegradation. As I said on the previous slide, hydrocarbons are susceptible to biodegradation, particularly the smaller and more mobile hydrocarbons, the volatile and soluble hydrocarbons being the most susceptible. The degree of susceptibility varies based on chemical structure, and particularly branching results in slower biodegradation. And typically there are residuals, so not all hydrocarbons degrade in a timely fashion into carbon dioxide and water. There are a wide range of conditions that are suitable for biodegradation in soils by naturally occurring microbes. Typically, under aerobic conditions, biodegradation proceeds rapidly. Something to keep in mind when we're thinking about soil vapor and vapor intrusion is that the biodegradation occurs in the water phase, so that's soil moisture and groundwater, not in the air or vapor phase. This slide serves as a reminder that for petroleum underground storage tanks, releases from those sites must be evaluated for vapor intrusion in accordance with the State Water Resources Control Board's low-threat UST case closure policy, rather than the SVIG. The technical basis for the approaches to petroleum vapor intrusion in the policy are described in this document entitled Technical Justification for Vapor Intrusion Media Specific Criteria. And this is a good resource on petroleum biodegradation and how that serves to limit the migration of vapors in the subsurface. Next up, let's talk about the two PVI screening approaches. So first, we have the separation distance approach. This relies on the potential for aerobic biodegradation, and it requires the presence of clean soil between the subsurface impacted media and the building in question. And it primarily uses soil and groundwater data in conjunction with empirically determined distances based on source type and strength. And there are two of those. So first we have non-aqueous phase liquid, or NAPL, and that separation distance is 30 feet. For dissolved sources, we have two separation distances, either 5 or 10 feet, based on the groundwater concentration, the strength, source strength, and the presence of oxygen. The other approach is called the soil gas oxygen approach, and it relies also on the potential for aerobic biodegradation. Similarly, it requires clean soil between the impacted media and receptor, and it primarily uses soil gas data where the soil gas samples are analyzed both for petroleum hydrocarbons as well as fixed gases, oxygen, carbon dioxide, and methane. Then the oxygen levels in soil gas are used to select a bioattenuation factor, or BAF, that is used in conjunction with the base attenuation factor. For situations where oxygen is less than 1%, you basically get no bioattenuation adjustment, so a BAF of 1. At 1% oxygen, you can use a bioattenuation factor of 0.1. So in this situation where you're using a soil gas attenuation factor of 0.03, that could be adjusted to be 0.003. And then at 4%, you get a BAF of 0.001. It's important to note that the BAF is not applied to subslab soil gas because biodegradation does not occur in the air or vapor phase. This slide presents a couple of separation distance cross-sections for NAPL sources. And these diagrams were borrowed from the low-threat UST case closure policy appendices. So on the left, we have a residence at the surface, and we have an mobile NAPL, on the groundwater table. And there is at least 30 feet of clean soil defined as total petroleum hydrocarbons, or TPH, less than 100 milligrams per kilogram between the source and the building foundation. And so this distance is considered, or has been demonstrated through numerous empirical studies, experience at petroleum UST sites, supported by modeling, but again, primarily empirical, that this is sufficient distance to attenuate petroleum hydrocarbon vapors in the subsurface. On the right, we have a similar diagram, except in this case, we are looking at residual or non-mobile LNAPL bound up in the soil, and there's at least 30 feet distance between the subsurface source and the building foundation. Something that's important to keep in mind is when we're using the SVIG for screening at petroleum-only sites, and specifically non-UST petroleum-only sites, is that in the step 1B.1 for building prioritization, you can substitute the 30-foot NAPL separation distance for the 100-foot distance that's mentioned for chlorinated releases. So now I'd like to describe our second PVI screening approach, which we call the soil gas oxygen screening approach. And to do that, I'm going to walk you through this conceptual PVI cross-section from US EPA to give you an idea how this biodegradation acts on the petroleum vapors to reduce concentrations. So this diagram is set up with increasing depth on the y-axis on the left, so you have the land surface at the top, and then you have your impact media at the bottom. And then on the x-axis, we have increasing concentration to the right that is used for these three different curves that are plotted. So let's start with the solid red curve, which is labeled PHCs and or petroleum hydrocarbons and CH4 methane. And so you can see just above the impacted soil, we have very high concentrations in the vapor phase. Throughout this kind of reddish reaction zone, those concentrations drop sharply. Typically in practice, this is orders of magnitude decreases over short distances, say a few feet, to the point where the concentrations of hydrocarbons essentially are non-detect by the time it reaches the land surface. On the right, we have this oxygen curve as a dashed blue curve, and you can see, as expected, concentrations of oxygen would be relatively high near the land surface and then decrease through the vadose zone and then sharply dropping through the reaction zone as the microbes use the oxygen in breaking down the hydrocarbons in the moisture phase. The dot dash green curve is for CO2 or carbon dioxide, and that's roughly kind of a mirror image of the oxygen curve. You can kind of think of that as a quality control check, perhaps. So in this approach, what you're really doing is you're investigating the extent of hydrocarbons in the soil vapor. And it's common to see the use of vertical soil gas profiles to kind of demonstrate that this type of breakdown is occurring, or attenuation is occurring. So you're additionally analyzing the soil gas samples for fixed gases, oxygen, carbon dioxide, and methane, in addition to the petroleum hydrocarbons. And then if there's sufficient oxygen present, then you can employ the appropriate bioattenuation factor. Wanted to give you an example of a real site. And so here we have a vertical soil gas profile at a crude oil pipeline release site where the crude oil had been mixed with a pressure distillate and had a high aromatic content. The LNAPL had spread down gradient and was actually beneath this crawl space home. The consultants went out and did multiple soil gas probe locations and collected samples at 3 depths at each location. And I've just selected a few of the constituents they analyzed for, which included TPH gas, which would represent the bulk hydrocarbon vapors, benzene, and oxygen. And so you can see just above the water table and the L NAPL, which I haven't really drawn in here, we have about 24 million micrograms per cubic meter of TPH gasoline. This is a fairly typical near source vapor concentration. Within 2.5 feet, we lose 3 orders of magnitude of concentration. So significant reduction over a very short distance. Benzene goes from near 80,000 micrograms per cubic meter at 7.5 feet to non-detect with a slightly elevated reporting limit at 5 feet. And then you can see, not a big surprise, oxygen is high in the vadose zone, but in the reaction zone down here at 7.5 feet, it's just 3%. And so this is a fairly typical example, but again, you can conduct this type of sampling at your own sites to see if this degree of attenuation of hydrocarbon vapors is occurring. So let's wrap up attachment 2, petroleum-specific considerations. And I want to leave you with a couple of thoughts on this. One is, when should we be most concerned about PVI? And one situation is when the subsurface source is close to the building, right? Another situation is if you've had large-scale releases of petroleum products and you have significant NAPL, significant source and strength. So it's not necessarily the site type, but the nature of the release that drives that potential for PVI. Wanted to point out that for evaluating VI for mixed chlorinated and petroleum releases, it's generally should treat them as a chlorinated release initially, or at least during the initial screening, steps 1 through 3, and then you reevaluate that during step 4, the refined risk assessment. Attachment 3 is entitled Sewers and Other Vapor Conduits as Preferential Pathways for Vapor Intrusion. This attachment is mainly focused on sewers and provides an overview on sewers, summarizes some studies demonstrating sewer or vapor conduit vapor intrusion, talks about how to collect sewer and vapor conduit air samples, and it also discusses approaches for evaluating sewer air. This cross-section presents a conceptual model for the sewer air and actually the vapor conduit VI pathway. So we have a residence with a basement, and you can see we have 2 different types of utilities. So on the left and on the kind of central bottom portion of the picture, we have the sewer in green, and then on the right-hand side, we have a land drain in purple. This land drain was designed to direct water and moisture away from the building. Here at the lower right, we have a VFC groundwater plume that is in contact with the pipes. And so VFCs, the groundwater contaminated with VFCs, is able to enter the pipes, and then the VFCs are able to directly volatilize into the airspace within these pipes, and then travel along the pipes and either get closer to the building to be released or potentially be released inside the building. For instance, faulty seals, P-traps, or damaged pipes, or via the floor drain, or potentially a break in the pipe, and then the vapors come in through the normal soil vapor intrusion pathway. So one of the key things to keep in mind here is that we're talking about transport through the airspace, not through backfill around these pipes. So as I mentioned on the opening slide, attachment 3 includes a description of sewers and a summary of studies where sewer VI or vapor conduit VI have been demonstrated. We recommend that you review these when you have time. For the next couple of slides, we're just going to talk about screening of vapors in sewer air and also sampling. So in 2018, the Environmental Security Technology Certification Program published 3 documents related to the sewer air vapor conduit VI pathway, and included a protocol for evaluating the threat. And this protocol is pretty helpful. So it starts with a desktop screening, which includes collecting and reviewing maps and drawings, identifying the locations and depths of sewers and utility conduits near release areas or groundwater plumes. for situations where those two intersect, or where those intersect, that represents a greater threat for this pathway to be active. Based on that, if your site works out to be a lower threat, you could start with a conventional VI investigation approach, which would essentially, for the SVIG, be step 2, soil gas. For greater threats, this would recommend additionally sampling sewer conduit air. However, in the context of the SVIG for greater threats, you would actually proceed to sampling indoor air via step 3, and you would consider whether or not to sample sewer vapor conduit air from the get-go, or perhaps you would include that at a later step if the initial round of indoor air results were difficult to interpret. So this sketch illustrates some potential sewer air sample locations. So there are manholes, cleanouts, and vents. I think from a practical standpoint or an easy physical access standpoint, cleanouts and manholes would be the best. Keep in mind that you would probably have to obtain access permission before sampling at any of these locations. So let's wrap up attachment 3 with some examples of options for sampling sewer air. So at the top left, we have sampling from a manhole, and in this particular drawing, a sumer canister is deployed at the surface, and then a long tube with a weight is placed down to just above the liquid level, and that's how the sample is collected. Another option might be to suspend a passive sampler to get this type of sample. On the right, we have sampling from a lateral or cleanout, again with a sumer canister and a tube running down the cleanout. And then over at the lower left, we have an example where essentially a tube with some sort of like modeling putty was used to seal the tube, and then it was snaked through a sink past the P-trap, and then somehow the modeling putty was dislodged so that the vapor or air sample could be collected. So these are just some examples, and there could be other ways to accomplish this. So SVIG attachment 4 describes groundwater as a line of evidence to evaluate vapor intrusion. This attachment includes the equations for groundwater to vapor partitioning and prediction of indoor air concentrations. It also provides some considerations for use of the groundwater line of evidence. In the next 3 slides, I'm going to walk you through the conceptual model for transport of vapors from the groundwater into indoor air. And we've got a cross-section that we're going to work through. So first up, I just want to give you the overall 2-step process for how we handle this mathematically. So first, we partition the VFCs in groundwater to vapor phase using equilibrium partitioning equations. And then second, the vapors have to migrate through the capillary fringe and the soil into the indoor air. We handle this through use of an attenuation factor. For our example, we're going to use tetrachloroethene, or PCE. And so you can see the diagram at the right, the PCE concentration in groundwater is 6.4 micrograms per liter. And so for this step 1, partitioning to the vapor phase in blue here, we're going to take the concentration in the groundwater, 6.4 micrograms per liter, and multiply that by the chemical specific unitless Henry's law constant, which you can get that from the US EPA RSL's chemical parameters table. And that comes out to be 4.6 micrograms per liter. That's not a typical unit we use for the vapor phase, right? And so we do a unit conversion, and we end up with 4,600 micrograms per cubic meter. Continuing on with our example, now we're going to take the concentration of vapors in equilibrium with the groundwater, 4,600 micrograms per cubic meter. Multiply that by an attenuation factor to represent the transport through the capillary fringe and the soil into the indoor air. And here we're using the US EPA groundwater attenuation factor of 0.001. And so that gives us a prediction or an estimate of the concentration of indoor air at 4.6 micrograms per cubic meter. So let's wrap up discussion of attachment 4 with considerations for when to use the groundwater line of evidence for vapor intrusion evaluations. So typically it's not our first choice when evaluating VI because of uncertainties about equilibrium partitioning and transport through the capillary fringe. So in general, if you have vadostone to work with, we would rather sample soil gas and directly measure what's in the vapor phase. However, if groundwater is shallow, the groundwater line of evidence may be our only viable subsurface line of evidence choice. When sampling groundwater for evaluating VI, the preferred sample location would be near the top of the water table. That's going to be most representative of what's going to partition into the vapor phase and transport towards a building. For situations where contaminated groundwater is in contact with the building, for instance, we're seeing a lot more subterranean garages these days, the US EPA groundwater attenuation factor may not be applicable.